Einstein's greatest legacy is not general relativity. It's not the photoelectric effect, and it's not slices of his brain. It's a word, Gedankenexperiment. That's German for thought experiment. Today, thought experiments are common in theoretical physics. We use them to examine the consequences of a theory beyond what is measurable with existing technology, but still measurable in principle. Thought experiments are useful to push a theory to its limits, and doing so can reveal inconsistencies in the theory or new effects. There are only two rules for thought experiments. A. Relevant is only what is measurable, and B. Do not fool yourself. This is not as easy as it sounds.
Before I start, let me just say a few words about myself. There we go. So, as Andrew told you, my name is Matthew Kleeman, and I'm the director of the Center for Cosmology and Particle Physics at New York University in New York. I did my PhD at Stanford, and then I went to the Institute for Advanced Study in Princeton, which is where Einstein went when he first moved to the US from Germany. So, what do? I'm a theoretical physicist. Well, when I'm not doing administration and when I'm not teaching, I'm a theoretical physicist. And that means I don't have a lab. And in fact, I don't look very much at experimental data. So I spend most of the day reading papers, writing papers, or trying to do calculations and usually failing. So this is a kind of science which is fairly unique to physics. These days, there's such a thing as theoretical biology. That's quite new. Historically, really, physics was the only science that had theoretical scientists. And maybe the most famous example of one is Einstein. So Einstein never did any experiments. He paid some attention to data, but mainly he thought about things and wrote down mathematical equations and tried to solve them.
Michio Kaku, what is the theory of everything?
The theory of everything is what drives hundreds of physicists around the world. And it could be the crowning achievement of 2,000 years of our investigation into the nature of matter. We want an equation, 1 inch long, that will allow us to, quote, read the mind of God. We want an equation that will summarize everything we know about the universe. Gravity, light, the electromagnetic force, the nuclear force. We want all of it into a single equation, which will give us not just the Big Bang, the formation of planets and galaxies, but even the formation of people, maybe even love. All of it in a theory that eluded Einstein for the last 30 years of his life. And today, we think we have it.
We do?
Yeah.
Why do we think that?
Because we have a theory called string theory. It is fantastic. It is incredible. It has astounded the world of mathematics and physics. And now you can't move in the physics world without bumping into somebody who wants to talk about the 10th dimension, the 11th dimension, the multiverse, hyperspace, time travel. All the things that were once considered science fiction are now centerpiece in our understanding of the nature of everything.
You called it a theory, however.
It's a theory because we are going to test it with the Large Hadron Collider. You know that Big Bang machine outside Geneva, Switzerland, that some people think is going to tear the world apart? Wrong. It's a machine of science. And we hope to create a mini Big Bang by slamming protons together near the speed of light, recreate a teeny-weeny bit of Genesis, and from that, extract information that will show us that perhaps string theory really is the theory of everything. And that's what I do for a living. That's my day job.
Where did string theory come from, and who's the founder of it?
You're not going to believe this. In science, we always say that you make observations, you have a theory, you go make more observations, and it's a very, very tedious process. Wrong. Nobody that I know of in my field uses the so-called scientific method. In our field, it's by the seat of your pants. It's leaps of logic. It's guesswork. There is a crisis in cosmology. Usually in science, if we're off by a factor of 2 or a factor of 10, we call that horrible. We say something's wrong with the theory. We're off by a factor of 10. However, in cosmology, we're off by a factor of 10 to the 120. That is 1
with 120 zeros after it. This is the largest mismatch between theory and experiment in the history of science.